Randomness in the ETH2 beacon chain. Right. So I guess to start off, I'll talk a bit about kind of what is randomness good for in the context of blockchains in general. And there's probably two major categories of use case here. So there's a protocol layer. And the protocol layer randomness is generally useful in the context of proof of stake, basically because proof of work kind of contains its own sort of built-in unpredictability in terms of selecting and kind of who chooses or who gets to create each block. But proof of stake doesn't have that kind of computational mechanism, and so you need some kind of randomness for choosing who gets to propose which block in a proof of stake system. And in the context of both proof of stake and sharding, kind of committee selection. So whenever you need to randomly sample some number of validators from a much larger set, you need some form of randomness. There's also application layer randomness. Application layer random sampling, so like for example, augur voting, fraud-proof lotteries, basically, and in addition to that, other games. So any kind of game that depends in any way on a random chance, you need, and where you want that game to run on the blockchain, either because it controls kind of the outcome of the game controls some assets, or just because like you want to have a game on the blockchain to kind of make the thing more trustless, then you need on-chain randomness of some kind. Now, what properties do we want, right? So clearly, on-chain randomness can't be truly kind of random in the mathematical sense of the word. It has to be a deterministic function because we need consensus on the output, right? It's a blockchain, we need consensus on every bit of the state, and if the randomness gets used by the blockchain, well, that's going to be part of the state. What we want is unpredictability, right? We want the number such that it's not possible to predict that number all the way right up until the moment that that number is released. Now, the main problem in these randomness designs is this kind of last manipulator problem, or I call it last mover advantage. So the idea is that there has to be some last actor that triggers the action that basically causes the state change that kind of goes from people not knowing what the, or the chain not knowing what the random result is to the chain knowing what the random result is. And this last actor basically inevitably knows that result first. And so they have this kind of manipulation vulnerability where they can choose to either publish that data or not publish it. And this potentially gives them a kind of the ability to manipulate the result, at least to a small extent. And so the question is basically, how do we kind of solve that problem? Early scheme, RANDAO. So this is something that has existed for quite a few years now. The basic idea is that you have some set of participants. Each participant in a kind of first round first publishes the hash of their seed, and then in the second round publishes their seed itself. And the seed that they publish kind of gets checked against the hash that they publish. And so in the second round, the decisions that each participant has, there's basically only one decision, right? To publish or not to publish. And the result of the RANDAO is basically, you take all of the results or all of the seeds that get published and kind of you add them or XOR them or whatever together, right? So it's fairly simple. There's a natural extension where if you want your hash commitments to be reusable, instead of using hashes, you commit to BLS pub keys, and then you basically kind of multiply the corresponding private key by, or rather you use the corresponding private key to just sign a message consisting of different epoch numbers, and BLS signatures have the property that there's exactly one valid signature for every given message, and so you can use that as a kind of a kind of commitment that you can just keep on opening in different ways over and over again for different rounds, but the mechanism is the same, right? So there it is in kind of 3 lines. The main problem here is, of course, and if you have these actors V1 to Vn, they publish the hashes and then they publish the values, but what if the last actor Vn never publishes Xn, right? The result is this, but what happens if the last actor never publishes Xn? And we can think about it in the context of, say, some kind of lottery, right? And imagine that one of the participants in this lottery also is actor Vn, and actor Vn um, sees x1 all the way up to xn minus 1, and then they see xn, that's because they generate it, but they see that with xn the result is unfavorable to them, right? So what they would do is they just like drop offline in their capacity as a RANDAO participant and just never publish xn. So how do we prevent this? The obvious answer is that VN never gets a reward and probably loses part of their deposit. The penalty probably can't be too high unless we allow a really long 1-week delay, basically because, well, if a VN never published XN, it could be because VN got censored. There could have been an attack on the chain. There could have been a DOS attack on VN or whatever. So there is a cap on how high the penalty can be to VN. But so in general, we can say kind of this actor VN has a 1 bit of manipulation power. They can either publish XN or they cannot publish XN. And if they don't publish XN, then, you know, presumably you'd have to start the mechanism again with a new set of actors. And this is at some medium cost. This is often good enough, right? So ETH2 phase 0 uses this mechanism, except it's done in this more kind of streamlined way where you have a whole bunch of validators, and every block proposer kind of basically does a RANDAO reveal as part of publishing a block. So instead of it being a kind of discrete in rounds, there's just this seed that constantly gets updated. And this is good enough for us because we need randomness seeds for some specific use cases. And there's only 2 requirements, which is 1, there can't be too much space for manipulation. So having 1 bit of manipulation power is fine, but having, you know, like 30 bits of manipulation power would be too much. And the reason for that is because for a committee selection, like for committees to be secure, it's okay to allow the committees to be kind of re-randomized a few times, but if you allow the attacker to just keep on grinding until they find a committee that's maximally favorable to them out of billions of possibilities, then potentially the kind of the safe committee size that you need to make sure the attacker can't take that over would increase by, you know, like maybe something like 40 or 50, right? So it would just cut down efficiency for us quite significantly. And then the second requirement is that manipulation should be more costly than the reward, right? So like, for example, if we're using randomness for committee selection and for block proposing, then if you can manipulate the randomness by 1 bit, then you can exercise, like, I think it's either 1 standard deviation or like, so I'm sure some mathematician could correct me, like O of 1 standard deviations, basically, in terms of kind of how many or how many more kind of positions you can give yourself in a particular committee. Now, of course, in ETH2, kind of we use this shuffling mechanism, so everyone's always in exactly 1 committee, but, you know, if you care about being in some committee more than being in other committees, plus the opportunity to propose a block. But in order to get these things, like, you have to make a guaranteed sacrifice of the reward for proposing a block right now, right? And so basically this kind is never worth it, right? Or is at least almost never worth it is the idea. More advanced randomness algorithms. So Ido Bentov came up with a lot of this. Instead of using this kind of commit reveal where everyone publishes data, you would, and then you XOR it, basically n actors each commit and reveal to 1 bit, and then the output is the majority. So if more actors reveal 1, the output's a 1. If more actors reveal 0, the output's a 0. On average, requires square root of n actors to fail to reveal. So basically, you need square root of n participants to kind of on-chain appear on a line to manipulate the mechanism. The downside is that if an attacker does control that much, they can attack reliably as opposed to just attacking 1 over square root of n of the time. So this is one way to kind of make an attack more expensive. We're not using this just because the complexity increase is not worth it. Now instead, we are, when ready, going to augment the RANDAO with verifiable delay functions. Yay! So quick recap of a VDFs, basically a function f of x equals y with the properties that, first of all, if you have x, anyone can compute y. Computing y requires a large minimum amount of sequential computation and beyond some points cannot be parallelized. And given y, you can easily verify that it's the correct output, or alternatively, like you might need a witness, but you get basically the same effect. Example of almost a VDF. Just repeatedly hash a number, right? You take x, you hash it once, you hash it again, you keep hashing it a whole bunch of millions of times. It's clear how to compute it. It's not parallelizable, but it's not easy to verify except by rerunning the function, right? So verifying is as expensive as computing. Slightly better example, inverse MIMC. So it's actually better to think about inverse MIMC by first talking about the inverse of inverse MIMC, which is regular MIMC. So start with a number, add a key, cube it, add another key, cube it, add another key, cube it, and so on and so forth. And the inverse of this, of course, is to start at the end, subtract, cube root, subtract, cube root, subtract, cube root, subtract. So like here we have it, right? Subtract, cube root, subtract, cube root. And this is modular cube rooting, right? So it's mapping 0 to p minus 1 to the set 0 to p minus 1. This is all done kind of modulo p. Cubing is much faster than cube rooting. It's basically about the speed increase is about the same as the number of bits in your field. So with, say, in a reasonable size field, the verifier could have a 100x advantage, or this could go even higher. So the idea would be that to compute the VDF, you would use this cube rooting function, and to verify it, instead of doing it forwards, verifying can be done by running the computation backwards. And there's an extension, which is the prover runs it forwards, and then the prover also runs it backwards, but then the prover makes a snark or a stark of running it backwards. And then you can definitely verify the snark or the stark quickly. So this is one path, and it's probably the easiest of the VDFs to understand. But there's also other VDFs. There's the repeated squaring-based ones. There's a lot of these functions. The Ethereum Foundation has a VDF and an ASIC project that we've talked about. So a lot of research going into this area, which is great. So why do we care about VDFs, right? Basically, we care about VDFs because we want to get rid of last mover advantage. So if one actor disappears, then someone else can compute the same function and they can get the same result, right? There's no kind of individual participant specific secrets that are getting released. And so there's no individual participant that the outcome kind of hinges on. Those with better hardware can, to a limited extent, learn the answer earlier than others, and this is a kind of challenge, and I'll talk about this. Need hardware analysis to determine kind of how long it takes to answer. But you can do a kind of crypto-economic game, right? You can kind of on-chain publish bounties for computing VDF outputs as quickly as possible, and thereby you can at least kind of have the system learn how quickly function can be computed with kind of public hardware. So randomness in the beacon chain, this is part of the kind of ETH2 annotated spec that I've been working on recently. So the idea is that the blockchain kind of proceeds in slots, and there exists this kind of RANDAO. So this is a kind of constant ongoing RANDAO where every slot someone reveals a commitment, and then that gets kind of XORed in, reveal a commitment, XORed in. And the RANDAO mix for one particular slot then gets used as the seed for a kind of 32 slots into the future. And we deliberately provide this look ahead of 32 slots basically because we want to give people some warning time so that even over here, they basically know what responsibilities they're going to have 32 slots, which is about 6 minutes into the future, so that they can, join the right P2P subnetworks, do some other calculations, like basically just prepare for whatever their responsibility is going to be. So this is the status quo, right? It's basically just a RANDAO where the output of that RANDAO goes into generating a seed, and then that seed goes into kind of random selection, and then combine that with the validator set, and you sample block proposers, and you sample all of these committees. We plan to kind of insert the VDF here, right? So instead of the RANDAO mix being the input for the seed, the VDF of the RANDAO mix is the input for the seed. Now, we will have to extend this from one epoch to kind of many more epochs. And this is why, right? Basically, so we assume that the attacker has some kind of advantage, right? Like basically, there's some speed at which you can compute the VDF with public hardware, and the attacker can compute the VDF kind of n times faster than everyone else. So n could be, I know people have different opinions. Some say 1.1, some say 4, some say 30, some say like 100. In the Ethereum team, we're definitely on the conservative side. Now, there's two attacks that you can use if you have an advantage, right? One attack is you compute the results within a single slot and use that answer to manipulate the RANDAO, right? So basically, if you're over here, then as soon as you see what the previous guy's RANDAO reveal is, and so you see what the previous RANDAO mix is, you know what your RANDAO reveal is, and so you know what your RANDAO mix is. And so if you can quickly compute the VDF within a single slot, then if you like the answer, you can publish your block. If you don't like the answer, you can skip your block. And so we're basically right back to kind of just having a RANDAO, right? So the reason why we combine a RANDAO with a VDF is so that even if the VDF breaks, we still have a kind of RANDAO level of security. Um, so that's the first attack. The second attack is you trick the network into thinking that your hardware is the public hardware, and then you disappear, right? And the idea behind disappearing is basically that after you disappear, kind of the network can't learn the answer in time. So here was a kind of diagram to see what the two attacks are. So right, if you see like this is a kind of single slot duration. So this is when you learn the other people's information that goes into the seed. This is your deadline for publishing. This is the kind of target VDF solution time, and this is the kind of target time for the protocol to learn the solution, because this is where the VDF solution actually gets used, right? And so the idea is that if the network kind of targets the VDF solution being published over here, and by target I just mean the network can kind of adjust what the difficulty of the VDF is, and it can adjust the number of rounds or whatever. So your first attack would be if you have an advantage, then you don't really reveal your hardware, and so the target time gets set based on not having your hardware, and then you use your hardware to compute it quickly, or alternatively you use your hardware and then you suddenly disappear, and the network just then doesn't have the ability to use a VDF output all the way up until kind of over here, right? So basically the challenge is then that kind of t use, so this minus kind of t start, this kind of difference in time between kind of the start of computing the VDF and using it needs to be the slot duration multiplied by kind of the attacker advantage squared. And that would basically motivate kind of why when we had the VDF, instead of using the RANDAO mix from one epoch ago, it would be the RANDAO mix from kind of quite a bit further back. So the use of the RANDAO and the VDF in ETH2. So the RANDAO will be used as an input into the seed. So the seed is kind of a hash that gets used to randomly select the proposer of blocks in the beacon chain and the shards in all of the different kind of functions. And it will also be used for committee selection, right? It'll be used for choosing these kind of random subsets of validators that get assigned to a particular responsibility to kind of verify and attest to a particular block. And then the VDF will also be accessible to the application layer as a randomness utility, right? So one nice thing about application layer use cases actually is that for a lot of application layer use cases, kind of you don't need this hard deadline. And so like for a lottery, for example, right, you can just have the answer whenever you have it. And so from a lottery's point of view, you can basically the time between request and the time between use actually is going to be here, right? But for these consensus layer applications, we do need to have a fixed time at which the answer actually gets used, and so there's this kind of advantage squared problem. So Yeah, and that's kind of roughly how RANDAO works, how VDFs work, how we plan to actually use the two in the Ethereum protocol, and kind of what basically what the use cases are for us. So thank you.